talked about two-column proofs where we lay out the logic of an argument completely. Coordinate proofs are a little bit different. They're a little bit less tedious and less thorough, but basically you just demonstrate what you want to prove. You use calculations to demonstrate what needs to be proven. So we're going to rely on the midpoint formula, the distance formula, and the slope formula to show whatever we need to prove. For this unit, we're actually really just going to rely on the distance formula. When we get to quadrilaterals and coordinate proofs within that unit, then we're going to be talking about midpoint and slope. For right now, we're really just going to be relying on the distance formula because we're going to be proving that sides are congruent. So we're using side, side, side in a coordinate proof to show that all three of our sets of sides are the same. So we're going to use the distance formula a lot in this first one. We don't actually only have to use side, side, side. This is just the first example. We could use all the other congruency theorems too. We'll show that in a second. But for right now, we're just dealing with side, side, side. So that means we want to show three pairs of sides are the same length. So we're going to find the length of PQ. I'm not going to fully show the distance formula. So the distance formula is x2 minus x1 squared plus y2 minus y1 squared. However, I don't want to have to write out those coordinates each time. I'm really just going to figure out the distance between each of the x-coordinates and the distance between each of the y-coordinates, and then square that value. So when I say that, I really mean I want to think about how far it is from 5 to negative 3. Well, that's 8. And then how far is it from negative 4 up to 7? That's 11. So square both of those values, you get 64 and 121. And then we add those together and we get 185. We might be able to simplify that. We could probably change it into a decimal too, but we don't really care about that. I just want to compare it to a side length from x, y, z. So I'm going to leave it exactly like that and see if it matches up with one of these side lengths. All right, then q to r. Between negative 3 and 0, that's 3 spaces, so 3 squared. Plus from 7 to 2, that's 5, so plus 5 squared. 3 squared is 9, 5 squared is 25, so together that's 34. If you'd like to use the coordinates and plug into the distance formula, you can. If you feel more comfortable doing it that way, go for it. Really, I'm just thinking about how far are each of them away from each other. That's what you're going to end up getting from subtracting the coordinates anyway. It might be a positive or a negative. I'm just always keeping it as positive because either way, when you square it, it ends up as a positive number. All right, then from P to R, so from there to there, from this x value to that x value, that's 5. From this y value to that y value, from negative 4 to 2, that's 6. Squaring 6, squaring 5, that gives us 61 underneath the square root symbol. I'm going to do the exact same thing with x, y, z. So from x to y, that's 11. From negative 1 to 7, that's 8. So not surprisingly, that's also the square root of 185. So that means that these two side lengths are congruent. Now from y to z, from 9 to 3 is 6. From 7 to 2 is 5. Add those together, we get 61. So that's actually going to match up with PR, and that's an important thing that we notice here. The order that they're given here is not always going to be the order that we're going to write our congruency statement in. So just because it says it's PQR and XYZ here, those letters aren't actually corresponding. P doesn't correspond with X, Q doesn't correspond with Y, so we don't want to write our congruency statement in that order. Now from X to Z, from negative 2 to 3 is 5. From negative 1 to 2 is 3. So we get the square root of 34 again. This is exactly what we're looking for. We get P and PQ and XY congruent. So since PQ is congruent to XY and QR is congruent to XZ and PR is congruent to YZ, we could say that these two triangles are congruent. when you're writing the congruency statement, I would suggest that you just draw this triangle, PQR, and label it with these side lines. Draw this triangle also, and label it with its side lines. Because you can see, as I oriented them here, they're not really corresponding. Like R doesn't really correspond with Z there. So if I write PQR, I'm going to say triangle PQR is congruent to, so from P to Q is going along that length of square root of 185, so it's this length. But then the next length, P to Q to R, that's square root of 34. So really I'm going this direction with it. It's Y to X to Z. By side, side, side. So there's a lot of flexibility in how you want to demonstrate this. Really, you just have to show the side lengths here. But this part needs to be specifically written like that. You have to say, since we have each of these three pairs of sides that are congruent, we could say these two triangles are congruent by side, side, side. All right, looking at example 2, kind of the same example, PQR and XYZ, we want to show if these are congruent. So I'm going to do PQ, QR, and PR, and then XY, YZ, and XZ. All right, PQ, from P to Q, that's 11 squared plus 10 squared. That's 121 plus 100, that's the square root of 221. From Q to R, from 4 to negative 2 is 6. From 9 down to negative 5 is 14. 14 squared is 196 plus 36 is 232. And then P to R, from negative 7 to negative 2 is 5. Negative 4 to negative 5 is just 4. 5 squared plus 4 squared is 41. Alright, so I have my side lines for PQR. For XY, that's a distance of 11. That's a distance of 10. So that's also the square root of 221. From Y to Z, 0 to 1, or sorry, negative 1 is just 1. And then negative 6 up to 3 is 9. So we square those two, and we get that is the square root of 82. And you notice that that doesn't show up anywhere here. So actually, I'm not even going to finish this. I know that these triangles can't be congruent because that side is not congruent to any of these three sides, which is exactly what I'm going to say. I'm going to say since YZ is not congruent to PQ, YZ is not congruent to QR, and YZ is not congruent to PR. Oops, I messed that up, but it doesn't matter. So since it's not congruent to any of those three, triangles are not congruent. So you're going to see sometimes where you have examples where they're just not congruent. You have to say that one of these sides, in this case it was YZ, doesn't match up with any of those three. That shows that this can't possibly be a congruent triangle. I'm going to let you try 3 on your own. It's more or less the same example as number 1. And I'm going to jump around on the back. I'm just going to do a few of these. You'll get the picture. Side, angle, side, angle, angle, side, and angle, side, angle. We're going to be given that these angles are congruent. So this example, we're talking about angle, side, angle. We're already given that 2 of these pairs of angles are congruent. Angle A is congruent to angle D. Angle C is congruent to angle F. We want to show by angle, side, angle that these two are congruent. So if we already have these pairs of angles, we just need to show that that side, AC, is congruent to this side, DF. So we're going to find AC first. And here I'm just going to count over 1, 2, 3 spots. Oh, I didn't mean to write the congruency symbol there. So it's over 3, and then up 1, 2, 3, 4. 3 squared plus 4 squared, that's 25. So AC has a length of 5. Do the same thing for DF. Going from here to there, going down 3 spots, over 4 spots. So you can see it's going to be the same. So that also has a length of 5. So we were given these two angles already. Now we just need to say since AC is congruent to DF, and we have that given information, then triangle ABC is congruent to A to B to C is the same as D to E to F by angle, side, angle. These are the two parts that you need to show. You need to show that you know that these two sides are the same, and since you know that they're the same, we could say that these triangles are congruent by that theorem. I think you can try these middle two on your own. 2 and 3, I think you could do. I'm just going to show 4 because it's a little bit different, but it's pretty much the same. We're told that angles B and D are right angles, and we want to prove that these two triangles are congruent by hypotenuse leg. So we need a hypotenuse and a leg. Doesn't actually matter which leg. We have 2 legs to choose from. We could use AB or BC. Doesn't matter. I'm going to choose BC. I'm just going to count. That's 2. We don't have to use the distance formula. We don't have to show that calculation. It's pretty apparent that that is just 2. Same thing with DF. We're just counting those 2 spaces. That's also 2. That's one of the legs. So we got the leg. Now we need the hypotenuse. That's got to be AC and EF. So from A to C, we're going down 4 over 2. Down 4 over 2. From E to F, we're going down 2 over 4. So those are both the square root of 20. Or 2 squared root of 5. Either way, you actually don't even need to take it to that step. That's apparent that those are equal. So since BC is congruent to DF and AC is congruent to EF, triangle ABC is congruent to A to B to C is the same as F to D, sorry, A to B, no, it's E to D to C. I just want to highlight that just to make sure. A to B to C is the same as E to D to F. Those triangles are congruent by hypotenuse leg. That is all you need to demonstrate for a coordinate proof.